Discuss about the what is reciprocity theorem, what is the superposition theorem, and what is Thevenin'S theorem. And we will do some problems are related to that theorems, that is superposition, reciprocity, and the Thevenin'S theorem. Now, in this class, I discuss some more problems depend upon the reciprocity and the Thevenin'S theorem, and we will go to the Norton'S theorem also. So reciprocity theorem in terms of AC circuits. The last class I discussed the one problem for depend upon the DC circuits. So verify the reciprocity theorem in the circuit. So you have to verify the reciprocity theorem in this circuit. For the voltage they given 10 at an angle of 90 degrees. So with 5 ohm resistor, 1 ohm resistor and J 2 ohm resistor and 4 ohms minus J 4 ohms. So there is the resistance and there is the capacitance and inductance. So reciprocity theorem must be there. So the magnitude must be there whenever you have to interchange the voltage and the current places. Also when you have to replace, the same will be magnitude will be obtained. That is called the reciprocity theorem. So for this, so in figure whatever you have taken, we have to find the impedance of the circuit across the voltage of 10 at an angle of 90 degrees volts. Here 4 ohm resistor is series with minus 4 ohm capacitor. When you observe these two are in series. So 4 and minus J4 are in series. Suppose the current I is flowing from this point. So the 5 ohms current at the 5 ohm resistor, the total current will be flow. So at this point, the current will be divided. So for this 1 ohm, they have to go some current, and 4 ohms, they have to go some current. So these 4 ohms, whatever the current will be flowing for 4 ohms, the same current will be flow at the minus J 4 ohms. And whatever the current will be flowing 1 ohm, the same current will be flow at the minus J 2 ohms. So here 4 and minus J4 are in series and 1 and J2 are in series. So and these combination are in parallel and the both will be series with the 5 ohm resistor. So first you have to find. So here 4 ohm resistor is in series with minus J4 ohm capacitor. Similarly 1 ohm resistor is in series with J2 ohm inductor. So these two branches are in parallel with each other and in series with 5 ohm resistor as shown in the figure. Now the combined impedance. So what is the total impedance? Total, generally when you have to find out in AC circuit, total resistance, equivalent resistance you have to find out. For DC circuit, same thing for AC circuit, total impedance you have to find. So what is the total impedance? ZEN, total impedance is equal to 5 plus 1 plus J4 into 4 minus J4, because the inductive nature and the capacitive nature are in parallel. So 1 plus J4 into, that is parallel means product of the impedances by sum of the impedances. So 1 plus J4 into 4 minus J4 by 1 plus J2 plus 4 minus J4. So that is equal to, so when the two, I already tell that when you have to multiply the two terms, both are in the polar form. When you have to add the two terms, both are in rectangular form. When you have to subtract the two terms, both are in rectangular form. When you have to divide the two terms, both are in polar form. So first, so for this 4 plus 1, 5 plus J2 minus J4, that is minus J2. Same thing. So for here we have to multiply. So first you have to convert this into the polar form and then you have to multiply this term. So first LCM, that is 5 minus J4 into 5 into 5 minus J4 plus 1 plus J2 into 4 minus J4, that is equal to 5 into 5, 25, 5 into 2 minus J10 plus, that is 4 minus J4 plus 8J plus 8. So total we get 37 minus J6 by 5 minus J2. So for this, so when you have to convert this into the polar form, then you get 37.48 at an angle of minus 9.21 by, when you have to take in the calculator, how you have to find out, how you have to convert the rectangular to polar and polar to rectangular means, if it will be the rectangular, 2 plus j3 is there, then how to convert into polar means, shift polar 2 comma minus 2 comma 3. Shift polar 2 plus j3 means 2 comma 3. 2 minus j3 means 2 comma minus 3. Shift polar 2 comma minus 3. 2 comma minus 3 equal to. Then you get the value of the magnitude and alpha tan equal to. Then you get the theta angle. In some calculate you get directly magnitude and phase. If some characters it does not get directly, so for that purpose shift polar 2 comma minus g equal to alpha tan equal to. Then you get the total magnitude and phase. Like that you have to convert rectangular to polar and polar to rectangular. So we get 37.48 at an angle of minus 9.21 by 5.385 at an angle of minus 21.8 degrees. So we get 6.96 at an angle of 12.59 degrees. So I dash is equal to 10 at an angle of 90 by 6.97 10. So that means when you have to be multiply, that means when you have to be divide, first you have to divide the magnitude and you have to subtract the phase angles. So 37.48 by 5.38, how much? 6.96. So minus 9.2 minus of minus plus 21.8, that is equal to 12.59. So total, what is the current flowing I dash is equal to total V by Z equivalent. What is V? 10 at an angle of 90 by 6.96 at an angle of 12.59. That is equal to 1.437 at an angle of 77.41. So now we get the current at the 1 plus whatever we have to get the current at this circuit, that is 1 plus j2 ohms. What we done, total current into opposite resistance. That means, so whatever for the reciprocity, when the voltage here, we have to find out I2 dash. When you find out that this current, total current according to current division rule, total current into opposite impedance, that is 1 plus j2 by total impedance, 1 plus j2 plus 4 minus j4. So I dash plus 1 plus j2 by 1 plus j2 plus 4 minus j4. So we get 1 plus j2. So what is the I dash? What you get? 1.437 at an angle of 77.41 into, you have to convert 1 plus j2, that is 2.236 at an angle of 63.43 by 1 plus 4, 5, j2 minus j4, that is minus j2. When you have to convert this, we get 5.385 at an angle of minus 21.8. So we get the value 0.597 at an angle of 162.64. So when you consider the voltage at the input and you have to find the current at the output. Now for the reciprocity theorem, so you have to reject, you have to put the voltage here and you have to find out the current at the input. So that what we do, first you have to, so the current will be flowing here. So here the current will be dividing. So 5 parallel, 5 and 1 plus j2 will be parallel. 5 into 1 plus j2 by 5 plus product of the impedance by sum of the impedance plus 4 minus j4. 4 minus j4. So we get 5 plus j10 by 6 plus j2 plus 4 minus j4. So 6 plus j2. So by 5 plus j4 plus 24 plus j8 minus j24 plus 8. So we get value 37 minus j6 by 6 plus j2. So you have to convert this in the form of the polar. So this 37.48 at an angle of minus 9.21 by 6.325 at an angle of 18.43. So we get the total impedance is 5.926 at an angle of minus 27.64. So I double dash is equal to 10 at an angle of 90. So that is the total what is the current flowing in the circuit will be total voltage by total impedance, 10 at an angle of 90 by 5.296 at an angle of minus 27.64. That is 1.687 at an angle of 117.64 amps. But we want the current at I2 dash. So I2 dash is equal to total current. So when you have to find out this current, what is the opposite resistance? 1 plus J2 by, according to current division rule, total current into opposite impedance by total impedance, that is 1 plus J2 by 1 plus J2 plus 5. So then you get 1.687 at an angle of, what is the total current flowing? It is 1.687 at an angle of 117.64 into 1 plus J2 means 2.236 at an angle of 63.4. That means we have to convert the rectangular form into polar by 1 plus 5, that is 6 plus J2 means 6.325 at an angle of 18.43. So how much you get the answer? 0.597 at an angle of 162.64. So when you observe here, whatever the when you have to take the reciprocity theorem, so the input voltage and output current you have to find. When you have to interchange also, the same current will be obtained. So in the last there is 0.597 at an angle of 162.64. And here when you have to interchange also, we get 0.597 at an angle of 162.64 amps. This is about the reciprocity example. Now we see about the Thevenin'S example. So already we have to know the Thevenin'S theorem. Thevenin'S theorem is in any linear network containing two or more voltage sources, current source or resistances, we have to consider one source in series with the one source voltage source, that is V.Th, in series with the single resistance Rth. Same thing for the AC circuits also, in any linear network containing two or more sources. So you have to consider one in any linear network, there are the number of voltage sources or current sources or resistance must be there. You have to replace it with the resistance. In terms of AC, we have taken impedance. You have to replace it with a single voltage source in series with the single impedance VTH and ZTH. So how you have to find out this Thevenin'S equivalent circuit of the network? So they have to find the Thevenin'S equivalent circuit of the network viewed from terminal AB. So I want to find out the Thevenin'S equivalent circuit from AB. I already tell that when you have to find out the Thevenin'S equivalent circuit, at what part they have to give across AB. So first you have to open that part. First you have to open that part. So when you have to be open that part, when you have to be open that part, so then remove 2 ohm resistor, set the voltage source to be 0. So then you have to be, then we have to be calculate the ZTH. Z1 is equal to, so when you have to find out for ZTH equal to whatever the open will be there, you have to open, and there is the short circuit must be there, voltage source will be there, so we have to short circuit. Then whatever the current will be flowing here, these 8 and 6 are in parallel. So that means here the impedances must be Z1 is equal to J into XL, that is J into 8, and Z2 equal to minus J XC because it is the capacitance. So put is minus J6. So here Z1, Z2 are in parallel. So ZTH is equal to Z1 Z2 by Z1 plus Z2. So 8 at an angle of 90 into 6 at an angle of minus 90 by 2 at an angle of 90. So that is equal to 8 into 6, 48, 90. When you have to multiply, both will be add. 90 plus minus 90, that is equal to 0 by 2 at an angle of 90. So 48 by 2, that is 24. When you have to divide, you have to subtract the angles. 0 minus 90. So it is minus 90 degrees. for finding the ZTH. Now you have to find out the VTH. How you have to find out? So you have to open that and then you have to find voltage across AB. Then whatever the parallel impedance must be there, you have to find the voltage there. Then you get the voltage across AB. So how you get? So when you have to find out the voltage across the 6 ohm resistor, the same voltage will become this VTH. So for that, so when you have to find out this, so apply KVL or you have to find out the equivalent impedance must be there, and you have to add that impedance and you have to find out the total current. Then you get the voltage across this. So apply KVL. So minus to plus, 10 at an angle of 0, plus to minus, minus 8 J8I, plus to minus, minus already this is capacitance, already there is minus must be there, minus of minus there is plus J6I equal to 0. So 10 at an angle of 0 is equal to J here what is 8 plus minus 8, it comes to plus and it will be goes to the minus, so it will be J2I. So I equal to 10 at an angle of 0 by 2 at an angle of 90, that is equal to 5 at an angle of minus 90. So what is the voltage across 6 ohm resistor means? Voltage across 6 ohm resistor means, so what is the voltage drop? I into R. So already you have to find out the current is 5 at an angle of minus 90 into what is the impedance value here? Minus J6. So we get the value will be 30 at an angle of minus 180 degrees. So there is in AC circuit, when there is impedance must be there, they given simply inductance, that is 8 ohms, but you have to convert it to inductive reactance, that means we have to put J8. When there is a capacitance, it will be only 6 ohms, put minus J6. Why you have to negative means in the inductance R plus JXL, that is the impedance for inductive nature, or minus JXC, it is represented by the capacitive nature. So we have to put J notation here. So we get VTH is 30 at an angle of minus 180 and ZTH is equal to 24 at an angle of minus 90. So we put VTH and ZTH. So if already there is a resistance, one resistance must be there in the problem, that is 2 ohms, then you have to put here, when you have to add this, then you get the total current also. So that is about the Thevenin's equivalent circuit. Now we discuss about the what is Norton's theorem. What is Norton's theorem? So Norton's theorem is similarly in some similar way in that of Thevenin's theorem. Norton's theorem is similar to Thevenin's theorem. It states that any two-terminal linear network or circuit can be represented with a equivalent network or circuit which consists of current source in parallel with a resistor, is known as the Norton's equivalent circuit. So a linear circuit may contain independent sources, dependent sources and resistors. So in the Thevenin's theorem, in any linear network containing current source, voltage sources or resistance must be there, you have to convert into a single voltage source with the series resistance. Here whatever the sources must be there or resistance must be there, we have to convert it to single current source in parallel with the single resistance. So Norton's equivalent circuit resembles a particular current source, hence it having a current source in parallel with a resistor. Current source in parallel with a resistor. So the current source present in the Norton's equivalent circuit is called as Norton's equivalent current or simply Norton's current. The current source present in the Norton's equivalent circuit is called as Norton's equivalent current or simply Norton's current. Norton's equivalent current or Norton's. In Thevenin's, it is Thevenin's voltage. Here we have to consider in the current source. So we get Norton's current IN. There it is VTH. and the resistor present in Norton's equivalent circuit is called Norton's equivalent circuit or equivalent resistor or simply Norton's resistor Rm. In the Thevenin'S, we have to take as Thevenin'S resistance. Here we have to consider the Norton's resistance. So in any linear network, if there is number of sources must be there or resistance must be there, you have to replace it with a single current source in parallel with the single resistance. So the single current source is nothing but Norton's current, single resistance is nothing but Norton's resistance. So what is the method to find the Norton's equivalent circuit? So first we have to take method 1. So follow these steps in order to find the Norton's equivalent circuit. Only the sources are independent. If there is already I am tell that in the Thevenin'S also there is independent nature and dependent natures must be there. So I also tell that there what is the method to find out the independent and dependent also. Here also there is a method to find out the independent type are present. So step 1, consider the circuit by opening the terminals with respect to which the Norton's equivalent circuit is found. So find the Norton's current IN by shorting the two terminal networks of the above circuit. So first whatever you have to find out. So first when you have to find out that two terminals, you have to short that and you have to find out the current. In the Thevenin'S, whatever the position you have there, you have to find out, you have to open there, but here you have to short. Find the Norton's resistance Rn across the terminals of the considered in step 1 by eliminating the independent sources present in it. Norton's resistance Rn will be the same as the Thevenin'S resistance RTH. That means whatever when you have to find out the Rn, so we have to open this terminal. Whatever you have to find out there, so you have to open that terminal, and the remaining sources, if there is voltage source must be there, you have to short. If there is current source must be there, you have to open, and you have to find out RL. The same way, whatever you have to find out the Thevenin'S equivalent circuit, the same way we have to find out in the Norton'S also. Step 4. Draw the equivalent circuit by connecting Norton's current IN in parallel with the Norton's resistance RN. So, whatever we have to find out, now you have to find out the Norton's current and Norton resistance. And then what we do, we have to put the Norton's current in parallel with the Norton's resistance. And if suppose we have to find out the any current, whatever you have to short there, now you have to put that resistance value in parallel and find out the Norton's current. So step 1 what we do, so whatever you have to find out at that portion, you have to short and you have to find out the Norton's current, and when you have to find out the Norton's resistance, the sources must be short and open, and whatever in where you have to find, you have to open that and find out the Norton's current. This Norton's resistance procedure is same as the Thevenin'S resistance. And then the last step, when you have to find out the Norton's current and Norton's resistance is connected in the parallel, and whatever you have value you have to find, you have to connect into the parallel. Then you have to find out the current across at this terminal. Now what is the method means, if there is both independent and dependent sources must be there. If suppose both independent and dependent source must be there, then what we do means, consider the circuit diagram by opening the terminals. So with the Norton's equivalent circuit is to be found. So opening at the terminals where we have to find out. Find the open circuit voltage. So you have to find out the open circuit voltage by using the VTH form. And find the Norton's current IN by shorting the two open. First you have to open and you have to find out VTH. And then open circuit voltage. And then you have to short and you have to find out the current. So for this Norton resistance Rn will be VOC, open circuit voltage by short circuit current. Open circuit voltage by short circuit current, that is Norton's current. So draw the Norton's equivalent circuit by connecting Norton's current IN in parallel with the Norton resistance RL. This is the procedure for finding the both independent type and dependent types are present. Finding the both independent and dependent types are present. And what is the method 3? This is another alternative method for finding the Norton's equivalent circuit. So find the Thevenin'S. Whatever procedure you have to find for the Thevenin'S, the same procedure you have to done here. That means you have to find VTH and you have to find RTH. And then what we do is, for source transformation technique. So already I am telling the source transformation technique. Source transformation technique means whenever the voltage source must be there, you have to convert into current source. That means we know the value of VTH and RTH, or we have to convert into the current. That is I equal to VTH by RTH. If suppose we know the current for the current and resistance value, then you have to find out current source must be there. Then you have to convert into the voltage source, like that. So when there is VTH or RTH, by using the Thevenin's equivalent circuit, you have to find. So you have to convert it in the form of Norton's. VTH by RTH is equal to current. I is equal to V by R, and whatever the value in the RTH, the same value you have to put connected in parallel, that is equal to Rn. RTH is equal to Rn. So this is the method for finding the another method way to finding the Norton's equivalent circuit. So I take a simple problem and have to find out the Norton's equivalent. Find Rn, In and current flowing through the load voltage across the load resistor by using Norton's. So I want to find out the I1 and Rn, and I want to also find out the current across AB, load resistance, that is 1.5 ohms. At the 1.5 ohms, I want to find out the current also. So for this, what first you do? When I want to find out the IN, first I want to short it. Where there it will be there, I want to short. So calculate the short circuit current. So how to calculate? We have shorted AB terminals to determine the Norton's current IN. So I have to short when the current will be flowing to 12 ohms. For 2 ohms the same current will be flow. For this point 6 and 3 are in parallel. So 6 into 3 by 6 plus 3 plus 2 ohms. So then the total current I is equal to V by R equivalent. So the total current will be there. I want to find out the current at 3 ohms, because whatever the current I want to find out, it is series with the 3 ohms. So total current into opposite resistance by total resistance is nothing but the total current flowing across short. So the 6 ohms and 3 ohms are then in parallel, and this parallel combination of 6 and 3 are in series with 2. 6 into 3 by 6 plus 3 plus 2, that is the equivalent resistance. So the total resistance in the circuit is 2 plus 6 parallel to 3 ohms. So total resistance is 2 plus 3 into 6 by 3 plus product of the resistance by sum of the resistance. So 2 plus 3 into 6, 18 by 3 plus 6, 9. So 18 by 9, that is 2. So that is equal to 4 ohms. So RT is equal to 4 ohms. So that is the resistance, but you have to find out the current. So for total current is equal to V by RT. So 12 volts by 4 ohms, that is equal to 3 amps. 3 amps. So now you have to find ISC, that is equal to IN due to current division rule. So the total current into, what is the total current? 3 amps into, what is the opposite resistance of this? 6. 6 by 3 plus 6, that is equal to 2 amps. 2 amps. This is the short circuit current. Short circuit current. So now you have to find out the total resistance. Now you have to find out the Norton's current we have to find out, and next you have to find out the Norton's resistance. So here what we do, total current, once again I repeat, total resistance equal to 2 plus 3 into 6 by 3 plus 6, that is equal to 4 ohms, that is the total resistance, and the current I is equal to V by RT, that is 12 by 4, that is equal to 3 amps. So according to the current division rule, total current is equal to total current into short circuit current is equal to total current into opposite resistance by total resistance. Next, now you have to calculate the open circuit resistance. So then you have to find out the Norton's resistance. Wherever you have to find, so you have to open that, and whatever the voltage source must be there, you have to short there. So we have to reduce the 12 volts DC source to 0 to replace the short circuit step 3 as shown in the figure. We can see 3 ohm resistor is in series with a combination of 6 ohm resistor. And so suppose I already put an arrow, so I have seen like this. When I have to see like this, the current will be flowing the 3 ohm resistor, then the current will be divided across 2 and 6. So when you have to find out the equivalent resistance, 2 is parallel to 6 and this combination is series with 3 ohm resistor. So 6 into 2 by 6 plus 2 plus 3. So how much it is? 4.5 ohms. This is the Norton's current. So we have to find out the Norton's current is 2 amps and in parallel with the Norton's resistance is 4.5 ohms. This is the, when they ask up to equivalent resistance, you have to consider from here point of view, 2 at an angle of 4. But they ask find out the current across 1.5 ohm resistor. So we already know the what is the current flowing in this circuit is 2 amps. But here the current will be divided to 4.5 and 1.5. So according to current division rule, IL is equal to total current, that is Norton's current is 2 into Norton's resistance, that is across this 4.5 by 4.5 plus 1.5. Total current into opposite resistance by total resistance. So for that we get the current with 1.5 amps. 1.5 amps. If suppose we know the current value and the resistance value we know, we have to find out the voltage. VL is equal to IL into RL, that is equal to 2.25 volts. That is equal to 2.25 volts. This is about the Norton's theorem. So for Thevenin'S theorem, if there is number of sources or resistance must be there, you have to consider the one source in series with the single resistance. In Norton's theorem, if there is number of sources and the resistance must be there, you have to consider one current source in parallel with the Norton's resistance. So when you have to find out the Thevenin'S, wherever you have to find, you have to, first step you have to open and find out the VTH. For finding the RTH, you have to open that part and whatever the sources must be there, you have to short when there is the voltage source, you have to open when there is the current source and then find out the RTH. For Norton's, wherever you have to find out, for that point you have to short, that is you have to find out the ion current. And for Norton's resistance, what we done means, wherever you have to find out, you have to open that and remaining sources must be short when there is voltage source and open when there is current source and find out the Norton's resistance. Norton's resistance is equal to the Thevenin'S resistance. This is up to some problems about the reciprocity and Thevenin'S and for AC and DC and then for Norton's theorem. Thank you.